This is Dr. J. Mohan. I'm going to talk about the transfer function of linear time invariant system in the subtopic of signals and stochastic processing subject. Today objective is transfer function of linear time invariant system, Fourier transform, Laplace transform of S domain, filter characteristics of linear systems, type of filter, signal bandwidth and system bandwidth. First we go for the transfer function of linear time invariant system. While we studying for the system, the transfer function depends upon the system character. Now we take for the linear time invariant system. The system is linear as well as a time invariant. That time what it will be going to happen, the transfer function. It is also going to follow further two kind of things. One is continuous time signal as well as a discrete time signal. Both the case we are going to study now. First we take for the continuous time linear time invariant system. It may be defined using the Laplace transform or Fourier transform. The transfer function of LTI system can be only defined under zero initial condition only. So why? Because of both Laplace and Laplace as well as a Fourier transform, it's going to work under the initial condition as 0. So that means if the system is going to consist of three kind of state. One is initial state, post response and present response. The initial state is represented as without giving any input, the system doesn't get to response. That is called for the initial state. That we represent as under zero initial condition. If we give for any post input, it's going to produce the output. That will be represented as a post response. The present response is represented as what kind of given input it is going to produce for the same kind of output. That is represented as a time invariant case. So based on that one, we are going to study for the under zero initial condition only in the transfer function of linear time invariant system. Now we take for the input, that is represented as x of t, is represented as a continuous time signal. X of t is represented as a continuous time signal. If we give the continuous time signal in the LTI system, it's going to produce the output as y of t. The system function is represented as h of t. This is, we know how h of t is came. By how h of t is came, then the input we give for the x of t equal to del of t, then produce the output is represented as the system function we represent for the t of del of t we represent. This t of del of t is called for h of t. This is, we know, previous session we studied. When h of t is represented as when we going to produce for the system response, as h of t is represented as a continuous time signal system response. That's why I represent as a linear time invariant system. It's going to work as a continuous time case in the sense h of t. And its produced output is represented as a y of t. Now y of t is equal to x of t into h of t. We call for the system output. So this is represented as a system output. Now we are going to study only this case, that is represented as a transfer function case, h of t. Now if I am going to take for the Fourier transform, that means the frequency domain or spectrum domain, that is called for the Fourier transform. It's represented as a x of omega, that is called for capital letter x of omega. Its response of LTI system is h of omega. As usual, we go for the system is going to get for the impulse input, its produce the output is represented as h of t. In the case of frequency domain is represented as h of omega. Its produce the output also is represented as a frequency response, that is called for the y of omega. Now the next state you take for the Laplace domain, that is x of s. Its response is represent as a system response is represented as a h of s, produce the output also y of s. Now I will write for the one by one for Fourier transform as well as of Laplace transform. Now capital letter y of omega is equal to x of omega into h of omega. This is represents a Fourier transform condition. Then Laplace transform condition, I represent for the y of s, capital letter y of s equal to x of s into h of s. So these are will be represented as system response of LTI systems. Now we go for the transfer function. The transfer function we call for the as a frequency response h of omega is a transfer function of linear time invariant system. Now the transfer function of LTI system is defined as ratio of Fourier transform of output signal to the Fourier transform of input signal. It's provide the initial condition are 0. Now the ratio between the output signal, what is it? See, in the previous case we represent for the equation is as a Fourier transform is like this one. Now we represent for the transfer function as h of omega as a frequency response. That is called for the Fourier transform of the inputs output signal is represented as a y of t divided by Fourier transform of the input signal x of t. This is the response of h of omega. Fourier transform of x of t is represented as a x of omega. The Fourier transform of y of t is represented as a y of omega. The finally we call for the transfer function of frequency domain in the Fourier transform is the ratio between the Fourier transform of output signal to the Fourier transform of input signal. In this case, initial condition, that means is represented as a, the x of t as initial condition is represented as 0. That means it's represented as a t equal to 0. There is no input we are going to given for the initially. Then only the system is going to represent as a transfer function of frequency domain. Or we can say another definition, the transfer function is defined as a ratio of output to the input frequency domain where initial condition are neglected. Or another case we represent for the transfer function of LTI system is Fourier transform of impulse response is represented as a transfer function of Fourier transform. That will be called h of omega is equal to y of omega divided by x of omega. This means ratio between output of Fourier transform as well as of input of Fourier transform in the signal. Now it's possible to find for the magnitude as well as a phase response. Why? Because of it's involved for both frequency response of negative part as well as a positive part of our signal. So we can identify for the exactly when the signal is going to respond. That's why what we are doing, we take for the magnitude as well as a phase response. The system function h of omega is equal to mod of h of omega e power j theta of omega. H of omega, that is mod of h of omega, we call for the magnitude response of LTI system. Then phase angle, that means phase response of LTI system is called for the theta of omega. The theta of omega I should write for the angle of h of omega. Next we go for the frequency spectrum of output is y of omega equal to h of omega into x of omega. Now the output magnitude spectrum we represent as a mod of y of omega is equal to mod of h of omega into mod of x of omega. That means the system response magnitude value into input signal magnitude value, both is getting to multiply, we get for the magnitude of output response we got. At the same time, we go for the phase response also. The phase response of output signal, that is represented as a frequency domain, is called for angle of y of omega is equal to angle of h of omega, that is system response, plus angle of input signal. It's both we added together. Then only is possible to get the phase of the output signal. Next, we go for the transfer function of LTI system as a conjugate symmetry property is going to get satisfied. Now, what I am doing, the transfer function, I take for the transfer function, I am going to give for the negative value of frequency, that is h of minus omega. It's produced the output is represented as a complex value of h of omega. This will be C in the Fourier transform properties. Now, we go for the magnitude response of conjugate symmetric condition is represented as a mod of h of minus omega equal to mod of h of omega. If we take for any negative value in the magnitude in the conjugate symmetry, what it's going to give for the positive value of your mod of h of omega. That's why what will be going to is going to, in fact, here you take for the negative frequency also, but it's going to produce the output as a only the positive values. So, if for example you take for the MRI signal, the MRI signal, it's going to display only the magnitude value. If the magnitude value were the more, it's going to represent as a white color, that is that white in the sense that is a gray matter. If the magnitude is value is very less, that will be going to have the dark color, that is represents a density tissue is going to present. So the best example is magnitude response of negative as well as a positive is MRI signal, that is magnetic resonance image signal. Next, we go for the phase response. The phase response of negative is represented as a angle of h of minus omega equal to minus of angle of h of omega. The impulse response of h of t of the LTI system is an inverse Fourier transform function. Now, we studied for the frequency response of system function h of omega equal to the ratio between capital letter y of omega divided by x of omega. So this is called for the frequency response of the function. Now, if you take for the inverse Fourier transform, we get for the h of t, that is h of omega. It's take for the inverse Fourier transform, we get for the continuous time signal. So due to that case, we need to have for the h of t in the sense you must take for the Fourier inverse transform of Fourier. This is f inverse is called for the Fourier inverse transform of h of omega. This is called for the impulse response of system function. Next, up to this much we studied for the frequency response or spectrum response. Now we go for the S domain. The S domain is called for the Laplace transform domain. As the system function, if you are giving for the input as a signal, that is called for the x of omega, x of s, that is a Laplace domain. It's produced output as, this is represented as a system response, that is h of s. System response is produced output is represented as a y of s. So now we take for the s domain, that s is represented as a complex signal, that is s is equal to some a plus of, or we represent for the alpha plus j omega. This will be seen while we going to Laplace transform studying the topic. So x of s is going to given the input, it's produced out to say y of s. It's the system response is called for the h of s. Now h of s, I need for the h of s. That h of s we need. So that's why what the output y of s is represented as a x of s into h of s. Now I need for this x of s. The x of s is represented as a y of s divided by x of s. So the Laplace domain h of s is called for the ratio between the Laplace transform of output signal divided by Laplace transform of input signal. We call for the Laplace domain or S domain of the signal. That is called for h of s equal to y of s divided by x of s. The impulse response, we need for the impulse response, that is h of t of the LTI system in the S domain in the Laplace transform of the transfer function h of s based h of t is equal to inverse Laplace transform, that is L inverse of h of s. So then we get for the h of t. This means we get for the original signal as a continuous time signal, in the sense for we receive for the h of s in the case you take for the inverse Laplace transform, we got for the h of t. So now we go for the relation between s domain as well as the frequency domain, that is h of s to h of omega, h of s to h of omega. So h of omega equal to h of s when s is equal to j omega. If you substitute s equal to j omega, automatically s domain is converted as a frequency domain. Or if you are going to substitute j omega in the case of s, then we get for the frequency domain. This is represents a relation between Laplace transform as well as a frequency transform in the case of Fourier condition. Next, we go for the filter characteristic of LTI system. So before we go for the filter characteristic of LTI system, we must know what is the system. The system only is doing for the filtering for the higher frequency or lower frequency, or it's going to have the middle frequency or anything is going to happen, that will be doing for the only system. So we know the system is represented as a h of t. We are going to given for the x of t. Its producer output is y of t. Now system in the sense this is represented as a system. So what we are going to make, what we are going to doing for the electronic devices, or what we are doing for the passive component, this component only is making to do the filter characters. So now the system is taking the input as a x of t. Its producer output is y of t. That means the system is going to perform some filtering action. That means it's going to happen for the reducing the frequency, that means or increasing the frequency component, that will be going to doing for the h of t. Now in this case, I take for the input as a x of t. Its producer response of the system is represented as a y of t, is characterized of system frequency domain in the s frequency domain as well as of s domain is y of s equal to h of s into x of s. This is represented as a Laplace domain or s domain, and the frequency domain or spectrum domain is represented as a y of omega is equal to h of omega into x of omega. Now h of s or h of omega is a transfer function of system. Now what will be, you take for the continuous time signal as x of t given, we take for the output is h of t, y of t. Now the transfer function is represented as a y of t divided by x of t, is represented as a h of t as a continuous time signal. And the same case, Fourier transform case, h of omega is represented as a y of omega divided by x of omega. So this is a Fourier case. Now we take for the Laplace transform, that is Laplace transform is represented as a system function h of s equal to the system response of Laplace transform in the y of s in the s domain divided by x of s. This are the case is going to represent for the transfer function. Now we go for the character. What are the characters? We know the filter is going to have the low pass filter, high pass filter, band pass filter, band stop filter, and as well as a band rejection filter. Now the transfer function h of s, how it's going to work as a low pass filter. You take for the LTI system, allow the transmission of only low frequency component and block all higher frequency component. Then the system is called for the low pass filter. Now I take for the graphical representation of low pass filter. What is it? Here I take for the magnitude value of system function, and here this side I am taking for the frequency response. This is a magnitude value of system function. Now Laplace transform domain we taken. So this is a system we given for the input as a Laplace of input. The system performance is H of S is produced Y of S. Now this is work as a low pass filter. Now I write for the H of S equal to what we going to represent Y of S divided by X of S as a Laplace domain. At the same time, the Fourier domain is represented as a H of omega equal to Y of omega divided by X of omega. Now you take for anyone, that's no problem. I take for the frequency domain, that is represented as a Fourier domain. Now we studied for the magnitude response of this one. Magnitude response in the sense mod of H of omega. The mod of H of omega is represented as an amplitude we called. Then the frequency response omega is represented as a omega is equal to 2 pi by f. Now I need for the f, that is 2 pi by omega I should write. Okay. So this is the frequency response. So based on the omega I represent for the frequency. For the x axis, y axis I take for the amplitude value is represented as a mod of H of omega. Now this case the system response, this is your what is it, this is H of omega, it's going to allow only the lower frequency up to certain level. See here we started for the minus 3 dB as a frequency level. This is minus 3 dB in the sense is going to maximum allowable case. Actually the conduction value it's going to happen for the H of omega equal to 0. The remaining it will be represented as a minus. Here will be have the positive direction. Okay. If up to minus 3 dB, the scale value of decibel up to minus 3 dB is going to conducting or pass the frequency. After that, the frequency level is getting to decreased. So now we got for the two different kind of bands. One is represented as a pass band and another one is getting as a stop band. Up to your 0 level, when they are going to touch with the 3 dB, what the frequency is going to happen, that is all it will be going to pass. That will be represented as a, if passed as a lower value of frequency, then the filter is called for the low pass frequency, low pass filter. That means lower frequency only is going to allow for our system response. This H of omega is going to transfer for only lower frequency. Then remaining case all frequency is getting to stop. Now where they are going to happen for this minus of 3 dB is going to touch for frequency response, that is called for the f of c. That is be represented as a conduction frequency. F of c is going to conduction frequency. Where it will be going to happen for the stop the frequency, that is called for the stop band frequency. So now the if you are going to use for the low pass filter, we get for the two kind of bandwidth. One is pass band as well as stop band. At the same time, we can identify for the where the frequency is going to conduct, where the frequency is going to stop. These are the parameters we know to learn from the low pass filter. Next case, we go for the high pass filter. The high pass filter is represented as the opposite of low pass filter. It's going to allow for the only higher frequency, is going to stop for the lower frequency. Here also I am going to take for the frequency response of Fourier transform condition. So the Fourier transform condition, magnitude response is represented as a mod of H of omega with frequency value we drawn for the graph. So here what it will be going to do, our LTI system is allow or transmit only the higher frequency component and block all lower frequency component. Then the system we represent as a high pass filter or HPF. Now we take for the x-axis for the frequency and y-axis is represented as a amplitude value, that is represented as a magnitude response. Then it started for the lower frequency. It's slightly is going to increase the frequency component. After that, it's going to get to saturated. So this means when the 3 dB up to 3 dB, the band is represented as a stop band. That is, then when the after 3 dB, all the frequency is going to transfer to the system through the output. So now here also we get for the pass band as well as stop band. The high pass filter, the pass band is infinitive and the stop band is going to have for the some limited value. But in this case of low pass filter, take for the low pass filter, the pass band is represented as a limited and the stop band is represented as a infinitive. So that's why previously I said low pass and high pass filter are inversely proportional together. The low pass filter is going to conduct only low frequency and high pass filter is conduct only high frequency. Next case, we go for the band pass filter. The LTI system allow transmission of only the particular band of frequency and block all other frequency component. Then the system is called for the band pass filter. Now we take for the Fourier transform only. We should draw the frequency as well as of magnitude response h of omega as well as of omega or f equal to 2 pi by omega. So here the frequency response is going to have for like this one. When the 3 dB is going to happen, for it's going to end for the 0 and the minus direction, that is a 3 decibel case. What will be going to happen? We can draw for one line. It's going to happen for the, it's going to, where they're going to touch in the first part, that is F1. Second part is going to represent as a F2 in the frequency level. So in between the F1 and F2, what the frequency is that system is going to pass. Otherwise, all frequencies getting to stop. So here we get for the two different stop band. One is lower side, lower frequency also getting to stop. Another one is higher frequency side also getting to stop. Only a certain frequency level we are going to transmit that in the system. This kind of filter is called for the band pass filter. In this band pass filter, it's going to have the bandwidth. That the bandwidth is represented as F2 minus of F1. What the frequency is present for the F2 as well as F1. Then Q point, it's the center point is represented as a Q point. That is called for the frequency is called for the F of 0. So this bandwidth is very, very important while we go for communication application. Most of the communication application they are using for the band pass filter. For lower application, they are going to using for the low pass filter. For higher application, is going to using for the high pass filter. So now we go for the another type of filter is called for the band rejection filter. In this band rejection filter, it's going to reject only the particular band of frequency and allow all other frequency component. Then the system is called for the band rejection filter or notch filter. So this notch filter or band rejection filter, how the filter response is going to happen. We take for the same Fourier transform of system function is represented as a h of omega. Then we take for the frequency response of the filter is represented as a f. We should draw for the frequency characteristics while we happen for the lower frequency is going to happen for in your filter response, like this one is going to happen. After that, it's going to take care of higher frequency component to transmit. Now we do for the 3 dB decibel condition in the attenuation. So where it's going to touch the case of our lower case, that is represented as a F1. The higher case of frequency is called for the F2. So now what will be happen? So in between the F1 and F2, the signals are getting to stop. That's why it's represented as a stopped bandwidth. The remaining portion is going to conduct. This is represented as a lower frequency also is getting to conduct. Higher frequency also is possible to conduct. So this is represented as a inverse condition of band pass filter. We call that is called as a band rejection filter. So now based on this one, what it will be going to doing for the band pass as well as band stop and band rejection case. The band of frequency component which is allowed by the filter is called for the pass band. So see here. So where the pass band is going to happen, the lower frequency as well as a higher frequency is infinitive. This portion is represented as a pass band. For here, the band pass filter, the pass band is represented as a in between the F1 and F2. So that's why I call for the bandwidth. For high pass filter, pass band is represented as where the f of C is getting. After that, all frequency is getting to passed. For the low pass filter, what will be happen when the 3 dB is going to where the touch in the frequency response? Here it will be going to happen the pass band. So that is 0 to FC is represented as a pass band. Like that will be going to happen for all pass band condition in the filters. So that's why I represent as a the band of frequency component which is allowed by the filter is called for the pass band. Next case, the band of frequency component which is not allowed to pass through the filter is called for the stop band or rejection band. So this is the way we represent as a pass band as well as a stop band or rejection band we may represent. Next case, signal bandwidth. Any particular signal has finite energy. The spectral component approach 0 when the frequency omega is tends to infinity. The spectral components can be neglected which have negligible energy. A band of frequency components it is selected which have most of the signal energy. Band of the frequency component which consists most of the signal energy is called for the signal bandwidth. Now you take for the low pass filter. Okay, you take for the low pass filter. What will be happen? It's going to here is attenuation is minus 3 dB. Here I represent as a h of omega is mod. Here is frequency. It is touch. It will be represented as a pass band, that is conduction band. This is represented as a pass band. This is pass band we called. The frequency between 0 to F C is represented as a pass band. Now what will be going to represent its component approach with 0 when the frequency omega tends to infinity. This frequency is represented as up to infinity is going to present. The spectral component can be negligible is represented as a negligible energy. The negligible energy where will be going to happen? The stop band condition is present for the negligible energy. But in the case of band pass, that is pass band condition, band of the frequency component is selected which most signal energy. This portion only is going to have the most energy is going to present. For example, we take for the voice communication, the voice, a human voice frequency is represented as 0 to 320 frequency, 320 Hz. In this 320, most of the energy is going to present. After 320, there is no energy. After 0, it will be doesn't have energy. In between, the most of the energy is there. The frequency level is very less. We can use for the low pass filter. The low pass filter is going to conducting only lower frequency. Okay, 0 to Fc. So the voice, how much voice is going to get in the frequency level 0 to 320 Hz frequency, it will be consist of most of the signals are present. That portion is represented as a most of the signal energy we call. So that is called for the band frequency component. Now how we represent as signal bandwidth? The band of the frequency component which consists of most of the signal energy. You take for the voice signal, most of the energy is present for the 0 to 320 Hz only. That signal we call for the signal bandwidth. So this is the way we represent as a signal bandwidth. Now we go for the system bandwidth. A system which has infinite bandwidth can be transmitted the signal without any distortion. The physical limitations are no system can be constructed that has infinite bandwidth. So most of the system we construct within the bandwidth. So that kind of system is represented as a system bandwidth. Now we take for here as a low pass filter or band pass filter, band rejection filter. What it will be going to represent for the minus of 3 dB? That minus of 3 dB is represented as a h of omega. How much need to transmit? That is a system response. How much need to transmit in the Fourier domain as a frequency domain? X of omega as input, y of omega as a output. So now this one it will be going to decide minus of 3 dB. So the attenuation is 3 dB. Then you see for the band rejection filter, the attenuation is 3 dB. We can identify for the two kind of pass bands. One is lower pass band, another one is a higher pass band. See the system response. It will be going to happen within the some limited period as a physical limit. No system can be constructed that the infinite bandwidth. This is the way we may represent as a system bandwidth. For here, the explanation, we take for the range of frequency over which a magnitude h of omega remaining with 1 by root 2 or with minus 3 dB is a maximum value, or the value at mid band is called for the band of the system. So we taken for the filter. This is h of omega as a mod. This is a frequency. Okay, this is represented as attenuation. So when 1 by root 2 or minus of 3 dB, so that is represented as a system bandwidth. It's going to allowing for the frequency levels. So the attenuation is minus 3 dB or 1 by root 2. Then the signal, what will be other frequency component? It will be going to as a low pass filter. We take here is a, this is represented as a, this is 0, this represented as a minus 3 dB or 1 by root 2. Then we draw for the one straight line. When it will be going to reach, that is represented as this component value is system allowable frequency. That's why we take for the system, that is a magnetic response, is the attenuation is present by 1 by root 2 or minus 3 dB of the maximum value, or the value at mid band is called for the band of the system. Next case, we go for the how the band of the system is specified, system bandwidth. Now we take for the one frequency component that is represented as a, we take for example of band pass filter. So now the magnitude response mod of h of omega as a Fourier transform, I represent as a mod of h of omega. The frequency response is represented as a spectral case of omega. Now the maximum magnitude is represented as a. This mod value I take for the A. So that's why I specified for the A. So then after the cutoff value 1 by root 2, I represent for here this 1 by root 2. It's present for the magnitude. That's why A by root 2 I represent. This is represents a frequency response of any system. For the we may draw for the graph based on the frequency response with respect of mod of h of omega as well as of omega. That is a system performance as well as a frequency or spectrum domain. We draw for the frequency response as this curve. So now as a 1 by root 2 of our magnitude in the A, in multiplication of A, that will be going to touch with the frequency of characteristics. In the attenuation level is represented as A by root 2. That value I call for the in the frequency level is omega 1. Next, where it will be going to happen as a higher case, as a frequency is decreasing case, is represented as omega 2. So the system is going to conduct only omega 1 to omega 2 frequency levels. So this is represented as a bandwidth of system. Now the bandwidth of system is equal to the higher frequency of omega 2 minus of omega 1. This higher frequency of omega 2 minus of omega in the bandwidth, it depends upon the attenuation characteristics of A by root 2. Now, omega n is called for the lower cutoff frequency or low off power frequency or lower 3 dB frequency. Omega 2 is called for the upper cutoff frequency or upper off power frequency or upper 3 dB frequency. Up to this much, I am going to complete it for the system response as well as the frequency response of system signal. Now, here we studied for the low pass filter as a system response as a low pass filter, high pass filter, band pass filter, band rejection filter, as well as a system bandwidth. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.